thing about Kilditch today. However, I'm going to try to present our results based on relatively classical or simple arguments based on Boltzmann equations. So I'm going to tell you the Boltzmann equation that we used, and then how we solve the Boltzmann equations and what we get from that. Yeah, so as I mentioned, the slides will be filled with equations. So, but I will try my best to explain every one of them. And if you have any questions, please feel free to interrupt and ask your question. Great. So let me start with graphene. So graphene is a two-dimensional material. So it's really a two-dimensional system with one atomic thick. So the thickness of the material is really one atomic thick. So it's really one atomic layers, and it consists of carbon atoms arrange themselves in a honeycomb lattice structure. So it's carbon arranged in a honeycomb structures. And the interesting features about graphene is that if you calculate the band structure or the energy dispersion relation of this system, it is not parabolic p squared to 2m, as you might have seen already in, for example, normal metal. However, the dispersion relation of graphene is linear-like cone shape, which is shown here in this schematic picture. And so at low energy, it consists of two energy bands. For undoped graphene, the chemical potential sits precisely here at the apex of the cones. So the lower band is completely filled. We call it valence band, and the upper band is completely empty. It is usually called conduction band. And yeah, so the Fermi energy sits precisely here at the crossing point. The nice thing about graphene is that it can be very easily doped. So you can shift the chemical potential up and down through the bands. And then if you shift it downward, then you get a system with a hole, with holes. If you shift it upward, then you have a system with electrons. Right. And it is described by these Hamiltonians. As I mentioned, it's not the usual non-relativistic Hamiltonian as we have seen in normal metal. It's not p squared over 2m, but instead it has this structure of relativistic electrons. So we have sigma, which is Pauli matrices dot momentum p, and then there is electronic speeds, Vf here. So if you have seen this type of structure, I mean, this is known as Dirac Hamiltonian. It is used to describe electrons, relativistic electrons in if you wish, in empty space in universe. However, usually for relativistic electron, as it moves with the speed of light, then these parameters here will be the factor c speed of light. However, as graphene is still non-relativistic system, electron in graphene doesn't move. An electron in graphene doesn't move with the speed of light, but instead it moves with another speed Vf, which is far less than the speed of light. So it's moved with the speed Vf, which is 100 times lesser than the speed of light. So in this sense, although the Hamiltonian that describes the system is relativistic one, electron in graphene still behave as a non-relativistic system. However, as the structure of the Hamiltonian is similar to the relativistic one, this is believed to be a platform, a down-to-earth platform where we can test all crazy ideas from relativistic systems that is either impossible to test or very costly to test with high energy facilities. Right. However, that's not the end of the story, because in addition to electrons in graphenes, similar to other solid state systems, there are other important ingredients that could play a role. So first of all, the samples that people synthesize might not be so perfect. There might be some irregularities or impurities or dirts inside the system. And those dirts can interact with the electrons and give rise to this potential energy here. So this potential energy is the interaction, the potential energy from the interaction between electrons and impurities. And usually this might play, and usually this play a very important role. For example, it might be the most important scattering mechanism for relaxing electric currents. The second ingredient is positively charged, right? So in contrast to relativistic electron that lives in empty space, electron in graphene do not live in empty space, but live in a lattice structure. So there is still a positively charged background on which electrons are living, and therefore those positively charged background do interact with electrons. And as zero order approximation, you can think about this positively charged background is a continuous Jellium models which neutralize the systems with electrons and give the whole system neutral. In the next order approximation, this could give rise to a dynamics and give rise to phonons. Right. So this positively charged background also interact with the electrons and give you some potential energies. So this is the if you wish, Coulomb interactions between positively charged backgrounds and with an electrons. Right. So that's the second ingredient. The third ingredient, which is very important for the talk today, is the Coulomb interactions. So we know pretty well that whenever we have charged particles, they do interact via Coulomb interactions, via Coulomb laws, 1/r Coulomb law, and that is basically these terms here. So so here you have, but the point is that in contrast to electrons, right? So electrons are confined in two-dimensional planes. So electrons can only live on the lattice. It cannot penetrate to the third directions, cannot go out from the sample. While electrons are confined into two-dimensional plane, Coulomb interaction live in 3 dimensions. So you can still have Coulomb interaction penetrates out of plane, right? So electrons do interact via Coulomb interactions, and the interactions between electrons is described by this term. So it's just Coulomb's law, if you wish, E squared. So this is potential energies for Coulomb force, E squared, where E is the electron charge, and then 1/r. And Right, so this is the Coulomb interactions between electrons. Usually in normal metal, interaction is very weak, not very weak, but is irrelevant, and then we can forget about Coulomb interaction altogether. We can model electrons in metal as if they are free particles. However, this is not the case here in this sample because Coulomb interaction turns out to be very important, very relevant, and very strong in the sense that if you calculate or if you estimate the ratio of Coulomb potential energy, if you compare this term to these terms, if you compare the potential energy to the kinetic energy, then the ratio is relatively high. That means Coulomb energy is relatively more important, if you wish, in this system than kinetic energy. And that implies that we cannot drop Coulomb potential here in this system. We have to take it into account. And that's what we are going to do today. So we are going to study the role of this term, the role of Coulomb interactions in this system. And that's why this system is known to be a strongly interacting, because Coulomb interaction is important. 2D because graphene is a two-dimensional material. It's one atomic thick system. Dirac materials. Dirac because the kinetic energy is described by Dirac Hamiltonian. And that's what it means. I'm not going to focus much on disorder and positively charged background, but they do play some important role. Great. So that's about graphene. And it's Hamiltonian. Now, let us move on to, let us discuss a bit more about Coulomb interactions, screening effects, and plasmons. So I'm going to take a perspective from these two gentlemen here, so David Bohms and David Pines. So David Bohms and David Pines wrote a series of papers since the 60s discussing the role of Coulomb interactions in three-dimensional electron gas. And they suggest that you can, well, Coulomb interactions in empty space is a long-range Coulomb interactions. It's 1/r interactions. However, if you put electrons in, for example, in metals, when you have many electrons, Coulomb interaction is not fully long-range anymore because in response to the interactions, electrons will try to rearrange themselves in such a way that the Coulomb interaction gets screened. And yeah, from this perspective, David Bohms and Pi suggest that you can split Coulomb interactions into two components. The long-range components, that's the first one, and the short-range component, that's the second one. The separation is not so clear, but usually it is set by Thomas Fermi's screening length scale. So as I show you here, so you have electrons, and usually around the electrons, you have basically electric fields due to Coulomb interactions. But you can split the interactions into two parts, the short-range parts and the long-range parts. And the separation scale is set by Thomas Fermi's screening length. Now, while the short-range interaction is responsible for the collisions between two electrons, right? I mean, if you have two electrons and then they move close to each other so that both of them are in the vicinity of the short-range interactions, then they do collide with each other, they do feel each other, and so on. So that's the role of the short-range interactions. However, the primary role of the long-range interactions is to incorporate heavy electrons and try to make them working together. And as a result of that, you get a collective modes, which is known as plasmons. Right, so the long-range interaction is responsible for the plasmon, and you can think of plasmon as a quantization or quantum particles of a shard oscillation. So you have shard oscillations in classical level, and if you quantize it, then you have a collective modes, which is known as plasmon. However, David Bowman-Pye found that in 3D material, plasmon is not very important. And the reason is that it has a huge gap. So plasmon are very massive modes in 3D system, and the dispersion relation or energy dispersion is given by plasma frequencies, which is proportional to the square root of electron density. So if you calculate the plasmon energy for, let's say, elementary materials, which is, for example, aluminum, of which the chemical potential or the Fermi energy is 11 to 07, the plasmon frequency is like much higher, or not much, but higher than the Fermi energies. So in the case of aluminum, plasmon energy dispersion is like 16 electron volts. So in that sense, as the plasmon energy is very high, it is very difficult to excite it with thermal energy. So what you have to do is to excite plasmon in 3D metal is usually to bombard the system with very fast moving electrons. So you have to give the system very high energies so that that match the plasma frequencies so that you can excite the plasmon. And you cannot excite a plasmon by thermal energies. And therefore, based on this argument, it was believed that plasmon is not important or is not relevant for normal metals in normal conditions. So in 3D metal, you can forget about plasmon altogether, and you can only focus on electrons interacting by short-range Coulomb interaction. If you wish, this is in the spirit of Landau Fermi liquid theory. However, this is not the case for 2D, as plasmon in 2D is gapless. So here I plot the energy dispersion of plasmon in 2D, especially for plasmon in graphene. So the vertical axis here is the energy. The horizontal axis here is the momentum. So this is energy momentum dispersion. As you can see here, the energy dispersion for plasmon in graphene follows a square root in momentum relation. So, and it is massless. I mean, at zero momentum, the energy is zero. So there is no gap. And therefore, you can expect to have a large amount, if you wish, of plasmon at normal condition. Well, to excite a gapless mode, you can excite it, for example, by thermal energy, right? You switch on energy and, well, in principle, they are there. So in contrast to plasmon in 3D metal, plasmon in 2D material is massless. And therefore, you can have a lot of them in normal conditions. And based on this argument, one should or one could expect that plasmon would be relevant and play some role, important or not, that are another questions, but it could play some role in the system. And that's basically the purpose of our works. We want to study the role of plasmons in graphenes. Especially, we want to investigate how plasmon plays role in transport properties, in thermal transport, in electrical transport. Great. Yes, so that's about dynamical screening, Coulomb interactions, and plasmon. So plasmon, in short, is an emergent particles from Coulomb interactions, from dynamical screened Coulomb interactions. Great. Now let me move on to electrons hydrodynamics. All right. So I mentioned in my previous slides that the long-range Coulomb interactions play a role in giving rise to plasmon. The short-range interactions play another important role, which give rise to electrons hydrodynamics. So electron hydrodynamic, as its name suggests, is a descriptions of electrons' behaviors based on hydrodynamic equations. So the assumptions for electron hydrodynamic is that you have many electron systems, and they behave somehow as if they are parts of a fluid or a water, So to understand why electrons behave as if they are part of a water, let us maybe think about water a bit more. So if you look at water, well, from macroscopic point of view, it is a continuous system. Right? But if you zoom in to the water, to microscopic scale, then water consists of water molecule H2O, and they bump into each other very frequently. Right? So water molecule bump into each other from time to very frequently. They exchange, dealing the collisions, momentum, and energies, but they will never lose their momentum and energy to the outside world. And as a result of this, as a result of the collisions, water molecule establish local equilibrium. Right? And then you can describe the system using a set of microscopic variables. For example, you can describe water by a few parameters like number density, momentum density, or energy density, or alternatively, you can describe water by its chemical potentials, fluid velocity, and temperatures. And this variable satisfies the conservation laws. For example, you have to, if you want to describe water dynamics, you have to write down mass conservation, momentum conservations, and energy conservations. And yeah, this variable is a basic variable in the sense that for others, I mean, once this variable is known, you can write down the other variables in terms of this variable. For example, if you are interested in electron current density, electric current density, then this is written in terms of charge density times velocity. So electron current is just charge density times velocity. Or if you're interested in momentum current, then momentum current is basically momentum density times velocity. Yeah, so this is momentum density, if you wish, and then times velocity. There is also, in the case of graphene, some internal effect here, which is due to Coulomb interactions. The first one is internal resistivity or internal conductivity, if you wish. And yeah, this is the results of interactions between electrons in the system. This parameter is known as viscosity. So it's viscosity is basically the properties of liquids, right? So yeah, so when electron is in hydrodynamic regimes, then it has these properties of water, which is viscosity. All right, and yeah, so that's the hydrodynamic of water. Now, if you want to have electrons hydrodynamics, what do we have to do? Right, because as I mentioned, you have a system consisting of many electrons, right? And difference from water molecules, electrons do not only collide with each other, but electrons also collide with impurities, also collide with phonons, and therefore it can not only exchange their momentum with each other, with other electrons, but it can also relax or give its momentum and energy to outside world. In this case, to impurity in the system, to phonon in the system. It lost its momentums and energies to the outside world. And this a priori make electron system behave differently from water molecules, because remember, when we talk about water just exchange their energy and momentum with each other. They can never lose their momentum and energy to the outside world. However, for the case of electrons, they can lose their energy and momentum to impurities and phonon to the outside world. Right. So to make electrons behave as if a fluid, what you have to do is you have to make sure that the losing of momentum and energy to the outside world is significantly and negligibly small. Or in other words, you have to make sure that the collisions between electrons is much, much more important than the collisions with impurities and phonons. And that is guaranteed by these conditions. So what these conditions mean is that the collisions between electrons is much, much more important than the collisions with impurities or phonons or outside world. And surprisingly, this condition has been achieved for graphene, because people managed to synthesize a very, very perfect graphene sample, meaning that the concentrations of impurities is relatively small, so that it's opened up a windows where impurity is not important. So, and in this window, electron-electron collision is much, much more important than the collisions with impurities. And therefore, you can have hydrodynamics regime here in this window where electrons behave as if it is a fluid. This window, though, is very fragile. I mean, it is a broad window, first of all, in temperature scale. It ranges from 20 to 100 Kelvin. If you go to very low temperature, however, impurities start dominating again. Coulomb interactions become less and less effective there. And in this regime, hydrodynamic is broken. However, if you go to very, very high temperature, then you start exciting a large number, let's say, of phonons, and therefore phonon will, and therefore electron can lose its energy and momentum to phonons to the outside world again. And in this regime, hydrodynamic is breakdown. It's broken down. So therefore, you can have hydrodynamic regime where electron behave as a fluid in a very, very restricted window. Having said that, however, people manage to observe this window in real sample. Great. Good. Right, so that's about electrons hydrodynamics. the take-home message, if you wish, is nothing but electron behave collectively as a fluid. And you use all the equations you use to describe fluid to describe electrons, which is not the case for normal metal, but it is the case here for graphene. Great. All right. Right, and one way to derive hydrodynamic equation, if you would, usually you can just write down hydrodynamic equations, but there's one way you can derive the hydrodynamic equation, which is from the Boltzmann equation. So Boltzmann equation is an equation of motion. You have many electrons, right? I mean, you might have heard this from statistical mechanics course, for example. You have many electrons. And if you are interested in hydrodynamics of electrons, then basically one way you can do, which is impossible, is you have to keep tracks on dynamics of every electrons. Right? You have to, if you would solve Newton's equations for every electrons, which is usually impossible in practice, because in normal metal, for example, you have a huge number of electrons, 10 to the power of 23 electrons in the system usually. And therefore, it is impossible to keep track on dynamics of each electrons independently one by one. Right? The best you can do is you can introduce another quantities, which is in this case distribution function. So distribution function describe the probability. So as you cannot keep track on electron by one, the best you can do is to study its probability, right? And that is described by distribution function. So the distribution function describes the probability that you will find an electron at a position r at a momentum k and at times t. So you don't care how each electron behaves independently. You only sit down and observe the probability that you will find one of them at a position r at momentum k and at time t. And that is described by this distribution function. Now that you have these quantities, and what you need is you need to know its equation of motion, how it changes with time. Right? And that equation of motion is basically this Boltzmann equation. I will come back to this later, but once you know the distribution function, you can calculate all observable you like. For example, if you want to calculate charge density, you can just take the probability, I mean, distribution function is the probability, and then you sum over all possible states. You have a probability that you will find electron of momentum k at times t and at position r. And if you want to know how many of electrons are there at position r and t, what you can do is you just have to look at the position r and time t, and then count all the electrons. Whatever state it is in, you count it. And this is basically this equation here, right? You take the distribution function and then you sum over all possible states at that position. So that gives you the number of electrons at position r and t. And if you want charge density, you just have to multiply the number density by the electric charge. And that gives you charge density. Similarly, if you want to calculate current density, for example, you just have to count the number of electrons. Right? And for electrons with state momentum k, then it moves with velocity, which is a function of k. Right? And the current is nothing but basically how fast the particle move. So therefore, you calculate this object here, the product of the current and the probability, and then you sum over all possible states. then you get the current density. And if you want electric current, you just have to multiply that current density to the electric charge. And then you get current density. So yeah, so once you know the distribution functions, you can calculate all observable you like. In this case, I show you a few examples, which is charge density and current density. Now you might want to ask yourself, but well, how these quantities behave in time or changes in time. And therefore you need an equations of motion. You need to know how the distribution function changes with time, similar to, if you wish, Newton's equation, right? In Newton's equation, you describe the system with its position, and you want to know how the positions of a particle changes with times, and that is governed by Newton's equation. Here you describe the system with distribution functions, the probability, and then you want to know how that probability changes with time, and that is governed by the Boltzmann equation, and which is this equation here. So let me explain you terms by terms. What does it mean by this equation? So first of all, you have this one, which is time derivative of the distribution function. So this describes how the distribution function, if you wish, changes with times. So that's the first term here. The second term here describes the following process. So you want to know how the probability changes with times, right? And there are basically three ways the probability changes with time. One is that you have a particles here at position R, and that then at some point particle move from the position R to the other positions. And this process changes the probability, right? Or you first have an empty, you first have an empty state at position R, right? No particles occupy the position R. And then there is a particle moving from other position to these positions. And that's also changed the probability of having particles at position R. So that's one of the process you can change the probability, and that is described by these terms here. Another way you can change the probability is by applying a force to the system. So let's say you have a particle occupying a momentum state K, and then you apply an external force to the system. And once you apply an external force to the system, then by Newton's law, momentum of the particle changes due to the force. And as the momentum changes due to the force, it move or excite to the other states. And that changed the probability of having a particle at momentum K, because once you apply the force to the system, electrons go from state K to the other state. So you lost an electron. And this process changed the probability. And this process is described by these terms here, where you apply an external force, to be more precise, electric force here in this case, and then it changed the probabilities of having momentum K. So it changed electrons' momentum to other momentums. So that these terms here. So there are three processes that can change the probability. The first one is that the probability is just varied with time. The second one is that electron move from one position to the other, and that also changed the probability of having a particle at position R. The third term describes the process where you apply an external force to the system. An electron was in the state of momentum K, but once you apply external force, it moved to the other state, and then you lost an electron from the state K as the electron moved to the other state. And as a result, the probability changes. And this process is described by this term here. You also have another process which look very scary here. And this process describes electron collisions. Right? Let's say you have electrons of momentum k, right, which is described by the distribution function f. So the probability of having electrons at momentum k. Now you ask yourself the question, what else you can change, what else you can do to change the momentum of the electrons? And let me tell you that another way you can do is you can bump this electron into other electrons. You bump this electron into other electrons, and then these electrons somehow exchange or give its momentum to these electrons, right? And as it gives its momentum to electron, it's go to other momentum states. And therefore, the probability of having electrons at momentum k changes because you first have electron as momentum k, and then it bump into another electrons, and then as a result, you have the going out electron with different momentum. So therefore, the probability changes within this process. And that is described by these scary terms here, which describe how electron changes as it collides with other electrons. Yeah, okay. I don't think I want to going into detail in this presentation, but if you want to learn more, either please feel free to ask questions, or we can also have a discussions after the presentations. I will be very happy to explain you in full glory, in full details, how we derive or what is the meaningful, what is the meaning of each terms here in the expressions. But I think for this, for the moment, you can understand this term as a change of the probability due to electron-electron collision. And yeah, I mean, in principle, if you want to understand the behavior of the system, what you have to do is you have to solve this equation. You solve it for distribution function. Let me take the analogy of Newton's law, right? I mean, if you want to understand the behavior of a motion of a particles, what you have to do is you have to solve the Newton's law of Newton's equation of motion, second law of Newton's, second law of Newton's second law, which is R double dot, I mean, second derivative of the position with respect to times equal to some force. And once you solve that equations, you have a solution, which is the position of the particle at times. And once you know the position of the particle, then you understand the system. It is pretty much similar here. You have an equations of motion for the distribution function. What you have to do is you have to solve these equations for the f. Right? It is relatively difficult compared to the Newton's law of motion here, because you have several derivatives of the f. You have also some integral of the f. So at the end of the day, what you really have to do is you have to solve these differential integral equations for the distribution function. And once you know the distribution function, you know everything about the system, because you can compute, as I mentioned at the beginning of this slide, any observable from the distribution functions. And okay, let me maybe skip this technical slides. And in fact, we have people have done so. For example, they take these equations and calculate electrical conductivity for graphene at charge neutrality points. And they find basically these specific results by solving this Boltzmann equation for graphene. They also calculate viscosity. Remember, I mean, now we are interested in graphene in hydrodynamic regime. So there is a viscosity describing graphene. They can also calculate viscosity by solving this Boltzmann equation, and they found these specific values of the viscosity. So this is viscosity of graphene, and this is electrical conductivity of graphene at charge neutrality points for undoped graphene. And this electrical conductivity and viscosity is a result, if you wish, of the Coulomb interactions, because Coulomb interaction describe the electron-electron interaction in this case. But they do not yet include plasmon, right? So if you wish, if you remember when I talk about Coulomb interactions, long-range and short-range Coulomb interactions based on Bohm and pi perspective, here they only include, if you wish, short-range Coulomb interactions. However, we do have long-range part of the Coulomb interaction, which give rise to plasmon. And that's what we are interested in this work. Let me skip this technical detail. We want to incorporate plasmon into the calculations. So therefore, we consider a system that is not only consisted of electrons, but also plasmon. Right. So therefore, we should have basically two equations. One describes the distribution functions or the probability of electrons. Another one is the distribution functions or the probability of plasmons. Right? So you have this equation here, which is basically the same as the previous one. So this describes how the distribution functions of electron changes with time. And yeah, as you have one additional particles, which is plasmon here, then you have one more equations, which tells you how the distribution functions of plasmon changes with time. And then you have the scary looking expressions which describe the collisions. Right? Well, again, if you want to understand it in full glory and details, I will be happy to discuss with you afterwards. But let me briefly tell you what it means physically. So this term is basically describe the collisions between electrons and plasmon. Basically, it describes how the distribution function change when electron collide with plasmon. These terms remain there, describe the electron-electron collisions via the short-range interactions. So this term was there in the previous slides. And this term describes how the plasmon distribution function changes as it collides with electrons. So this scaly looking expression describes basically how the distribution function changes via the collision processes. And then again, if we want to calculate any observable, what we have to do basically is to solve this couple of the equations, which is a challenging problem because if you look into the expressions, then you have several derivative terms of F and B. So B is the distribution functions of plasmon, F is the distribution function of electrons, and then you have F and B inside the integral, right? So you have F here, and then you have also B here. And you have, for the B equation, you have B here, and you also have F here. Oops, and they are inside the integral, right? So at the end of the day, you have nonlinear equations, and they do couple with each other, and then you really have to solve this couple of equation to get the distribution functions of electrons and plasmon. And once you have distribution functions of electron and plasmon, then you can calculate any observable you like. You can understand the behavior of the system. And that's what we did actually. We solved this system of equations. I think let me skip the details and let me just show you our results. So we solve this couple of equations and then calculate electrical conductivity and thermal conductivity of the system as a function of doping. So what I show you here is the first picture here is the first plot here is the electrical conductivity. So the vertical axis is electrical conductivity as a function of chemical potential. So the horizontal axis is the chemical potential, which determines charge density of the system. When mu equals 0, then you have the undoped graphene, right? So undoped graphene is basically here at mu equals 0. And we solve this, we calculate electrical conductivity for two scenarios. One is the scenario with plasmon, and two, the scenario without plasmon. So we studied two scenarios, with plasmon and without plasmon. So for those two scenarios, we calculate electrical conductivity, and surprisingly, we find that the plots or the electrical conductivity for two scenarios for top or sits precisely on top of each other. And what it means is that either you have plasmon in the system or not, it's not important for electrical conductivity. Either you include plasmon or not, then electrical conductivity does not change. And yeah, that's probably makes sense if you think about it, because to measure or to calculate electrical conductivity, what you can do is you take system, you hook it up to a battery, you hook it up to batteries, and then you let electric current flow, right? And as plasmons are charge neutral, then they do not respond to electric field, right? So either you include plasmon or not here is not important, because plasmon do not give any additional contribution to electrical current anyway, and therefore the current charge current does not change, and so therefore you can expect that electrical conductivity does not change by the inclusion of plasmon, and that's actually what we see here. Plasmon does not change the curve. However, if you calculate thermal conductivity, then we see that plasmon give a sizable contribution. So again, we solve the Boltzmann equation for two scenarios with and without plasmon. And then we calculate thermal conductivity as shown here in this plot. So the vertical axis is thermal conductivity. The horizontal axis is again chemical potential, which determines or which is set, if you wish, by electron densities. For undoped graphene, the chemical potential sits precisely here at mu equals 0. And we solve the Boltzmann equation for two scenarios. The first scenario is the red curve here, where we do not include plasmon into the equation. And the second scenario is the blue curve here, where we include plasmon in the calculation. And as you can see, plasmon, when we include plasmon, then thermal conductivity change significantly. So therefore, plasmon give quite sizable contribution to thermal transport. And why is that so? We can understand it from this simple schematic picture. So if you want to measure thermal conductivity, what you have to do is you have to attach your sample with heat bath, right? So you have a sink and source. You have source and sinks of heat currents, and then once you attach your sample to the bath, then to the hot and cold bath, then the system will try to move from I think this is the wrong direction. The system will try to move from the cold to the hot bath. And yeah, so as a result, it gives rise to energy currents and heat currents. And all the particles can participate in this process, right? I mean, electrons can carry heat current, plasmon as well can carry heat currents, and therefore, if you neglect the plasmon, basically you drop the plasmon contribution to heat current. But if you include plasmon, then you give one additional contributions from an additional quasi-particles, and that's basically what you see here. So plasmon really give a sizable contribution to thermal conductivity. Right, and I think with that, I think I will stop here, but let me maybe summarize the main message that you can take from the presentation today. And the message is that if you have a system with Coulomb interactions, then especially for 2D, then you have additional quasi-particles, which is known as plasmon. And in some conditions, especially in the hydrodynamic regime, plasmon could give a sizable contributions, especially to, for example, thermal conductivity. So plasmon can play a role in some observable, and in general, you cannot neglect the contributions of plasmons. And this is in contrast to 3D, where you can always neglect the contributions of plasmon. Right. With that, yeah, let me stop here. And this work has been done when I was a PhD student in Utrecht University together with these gentlemen. And let me also take this opportunity to acknowledge them. So Laufitz and Hengstuf were my PhD supervisors. Tim Ludwig, Pedro Emanuele, and Simonas. Tim was a postdoc in the group, and Pedro, Emanuel, and Simonos were PhD in the group. And they are from Utrecht University in the Netherlands. Right. With that, let me thank you all again for coming. If you have any questions, I will be very happy to take them all. Thank you very much.
Yeah, thank you, Kitinan, for your presentation.
Yeah.
Okay, thank you very much for your presentation.
You're welcome.
Is there any question? Is there any question from the audience? Okay, if not, then Sorry. So yeah, so it's quite interesting what you have done. So can you tell me? I mean, it's my personal question is, so can you back to the like which regime the hydrodynamics of the electron is important? I mean,
You mean this one?
it's very basic one. I mean, yeah,
This one.
yeah.
And what is your question again?
So when I mean in one kind of case, the hydrodynamics is important, and which one is, for example, for the in your graph, I think you saw that in the intermediate temperature, the hydrodynamic regime is important. However, I
Yes.
think most of the thermoelectric phenomena is observed in room temperature, right?
That's true, and that's true, and that's why usually in let's say in 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 the other materials, you when you want to calculate thermoelectric coefficients, for example, you do not have to include, if you wish, Coulomb interactions, right? Usually you can calculate it within the relaxation times approximation, if you wish, and the relaxation time is usually described the relaxations of the momentum relaxation of your system, either to impurities or phonons. But that's in a way already ruined if you reach the hydrodynamic regimes, because momentum relaxation to the outside world is much more important than the exchange of the momentum and energy between electrons themselves. And that's, if you wish, violates the hydrodynamic conditions. It means that if you go to very, very high temperatures and you have a lot of phonons, for example, and then electrons collisions with each other is less frequent compared to electron collisions with phonons. And in this sense, momentum is not conserved. Momentum and energy is not conserved anymore among electron, but lost to the outside world, and in this case, phonon bath.
Okay.
And that's why you cannot achieve, if you wish, hydrodynamics in.
Yes. Is there any limitation for the? So you apply your model to graphene, right? So
Yes.
In graphene, is it still this graph still holds true? I mean, does the temperature limitation of this model is still the same in graphene, or?
Indeed, but yes, indeed, but I think some of the experiments.
Because this L0 equal P squared divided by 3 kb per E is for three-dimensional system, right?
Oh, right. But Wiedemann-Franz law is
for three dimension. The 2 dimension is different, has a little bit different form.
Is that the question or statement?
Yeah, no, I'm that's the statement. I mean, the statement that L0 is different from for 3D and 2D and 1D. So it's because of the Fermi distribution and density of state is different. So my question is how should we modify this? So is this graph? This graph is for three-dimensional system, but if you apply
it, this graph is for two-dimensional system. Then, if you say so, it's interesting because, as far as I know, Wiedemann-Franz law in 2D is not different. In a sense that,
the classical one
is one. Or also for
yes, I understand KB, but the factor P square by 3, I think it's a little bit different. But that will affect the temperature, the critical temperature that you mentioned. It's not 20 and 100 anymore. it may be like larger or smaller. That's my point. I mean, this is for the 2D is around 20 and for 3D it's from 20 Kelvin to 100 Kelvin. But for 2D in graphene, for example, how is it more important? I mean, is it more large, the domain of hydrodynamic regime, or is it more narrow? It's very basic question. I mean, I'm sorry.
No. It's interesting question. No. So maybe I didn't make it clear enough, but this is really, first of all, for graphene. So it's 2D.
No, it's for graphene. It's for 2D. Okay.
It's about graphene. It's 2D, and this is really the window where you can observe hydrodynamic regime in graphene. But okay, and my worry is now about this Lorentz ratio, because as far as I know, even for 2D or graphene, even for 2D and for graphene especially, the Lorentz number is still pi square over 3.
Yeah, we can do that, even though it's 2-dimensional.
We can discuss that.
Electron can still move through the
this graph is really for graphene. This graph is for graphene.
So, okay, then my other question is, I think in the whole your presentation, you focus on the like conservative current, right? Current which follow the conservation law. So thus the scattering will give some kind of dissipative current, which will not give the conservation law equal to 0. Current is always.
I think you're right. I think you're right. So
in fact, yes.
In fact, yes, we have included. If you're completely right. I think we have included a small concentrations of impurities here. I mean, otherwise, thermal conductivity would diverge.
Right? Yes.
So in order to have finite conductivity at all, then we need a small amount of impurities, and we have included that. However, we have included in a way that the relaxation time due to electron impurity collision is much smaller compared to the collision times due to electron collisions. So yeah, in that sense, there is impurity, there is electron impurity collision here in these plots, but very small. Just to make sure that the hydrodynamic regime is not completely, which breaks down due to impurities. If you have too much impurities, then you end up with the other regime where thermal conductivity follows basically the Wiedemann-Franz law.
Yeah. So yeah, my point is that because in the conservation law, I think you have 3 conservation laws, right? So there are for
right,
the
we have 3 conservation laws.
Momentum, and for what the other ones?
There are charge, momentum, and energy.
Okay, yeah. For the momentum, I understand it's the basic law, but for the energy, I think for heat energy can dissipate. I mean, it's dissipative. It's in entropically speaking, it's not really conserved. I think.
Yeah.
So I think in the most basic of system, I think there are always Joule heating, and this Joule heating cannot be written in conservation law, right?
You're completely right. I think I am a bit sloppy here, but in principle, I'm a bit sloppy here, but you're completely right.
Hey, you were a student, don't worry.
If you apply the electric field, for example, here on this side of the energy conservation, you would have a term like J dot E, which is Joule heating. And for the momentum conservations, okay, momentum conservation does not affect, of course, but yeah, in principle, you are right. For the energy conservation, with this term here, you will get Joule heating, which is just E dot J, electric field dots, electric currents.
Okay.
So that is actually, it's not actually conserved in that sense, but it's conserved up to the Joule heating. If you apply the external force, then okay, it's the conservation law breaks anyway, right? But if you do not have external forces at all, then they conserve. But okay, I think you are completely right. I'm obviously
Okay.
yeah.
Yeah, thank you very much. I think that's yeah, I will read your publication further, I think. Is there any other question for other audience? Any question for Ansel? Seno? No question? Okay, I think if there is no question, and thank you
Okay.
very much, Kitinan, for your presentation.
Okay,
You'll
thank you very much.
in touch, yeah. Oh yeah, email or any thing. Okay. So before we close this session, maybe I can ask Januar, Pak Januar, can you share the can you keep the some certificate, Pak Januar? No, Mbak.
So you're not talking to me, right?
No, 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 no.
Okay.
Okay, not then. Sorry. So it's okay. So okay, maybe he is busy. So in our department, so at the end of the seminar, we will give some kind of certificate to
Oh,
the
okay.
presenter. So let me share the screen, and usually there will be a senior lecturer that gives the certificate, but
Okay.
yeah. Then I think I will give the results. Okay. Wait a minute. Okay, so thank you very much, Kitinan, for your presentation. And on behalf of the Department of Physics, we say thank you. And this certificate is awarded to Dr. Kitinan Pongsangangan in recognition of the valuable Dirac system in hydrodynamic regime. The role of the dynamic in dynamical screening and plasma. Okay, so yeah, actually we have usually we have some photo session if we are offline, but it's online. I
Okay.
think the screenshot is already taken by the uh by the by the faculty. So thank you very much again, Kitinan, for your presentation. And
You're really welcome.
yeah, I think I really want to ask about plasmon more. I think, but uh the expert is not here today, so I think I cannot ask about that more. So think
Okay.
we will get in touch with via email or via Ines, and then we can do more research together in the later time. So thank you very much, Kitina, for your presentation, and I hope everyone will continue to follow our channel here in the Department of Physics in YouTube, and please share this video, and please see you again in the next seminars. Thank you very much all, especially Dr. Kitina.
Okay. Bye bye.
Bye bye. Thank you very much again.
You're welcome.